Recording in
All
progress.
right, welcome everybody to our continuing conversation about acids, bases, their dissociation equilibria, and now finally the conversation about pH. So we have talked about pH before in lab, but let's just ensure that we review this so we're totally comfortable with the idea of what pH is and how it differs from our idea of a strong versus weak acid or base. So I have highlighted here that when we are talking about like acidity or alkalinity, so acidity, how acidic? Or alkalinity, how basic? A solution is. Depends on the concentration of either H3O plus and or hydroxide ion dissolved in solution or present in solution, where again, this idea of these dissociation products being present in solution is a result of our HA and B dissociation equilibrium. So what I'm trying to say here is like if I were to hand you a beaker of strong acid, but it was 1.0 times 10 to the negative 4 molar versus weak acid that had a concentration of 1.0 times 10 to the positive 4 molar, we would expect these two solutions to have different levels of acidity. And I think we kind of intuitively understand that this level of acidity is not necessarily always going to correlate with whether we have a strong or weak acid present, but rather how much of our acidic particles are present. So of course, this is going to require some analysis of like the actual amount of acid particles or base particles when talking about basicity that are present in solution as a result of our dissociation equilibrium. But in this extreme example here, assuming like, not an insane disparity in Ka values, like let's say this had a Ka of 10 to the 3 and a Ka of 10. Because this one is more concentrated, in H3O plus, this would be a more acidic solution. So there's more H3O plus in this solution than perhaps in this one. This is very qualitative kind of general example, but the idea is that just because you're a strong acid doesn't mean you're always going to create a super acidic solution. It's very likely that you will because you're good at dissociating and creating that hydronium ion. But the point is that concentration is the determining factor when it comes to determining the acidity or basicity in solution. So this depends on concentration. Now, this concentration dependence is actually a really significant one. That's why I'm, really emphasizing this distinction here, because normally we've been looking at kind of like modeled trends between two variables that we look at that are linear, right? There's a direct proportionality that might exist between some variable X and another variable Y. However, when it comes to the idea of like how does the concentration of acid, for example, impact what like you and I perceive as the acidity of the solution, turns out this is an exponential relationship. So if I were to look at the acidity of solution plotted against the concentration of acid, I would see that as my concentration of acid increased, my acidity would increase wildly, specifically in a 10 to the x exponential relationship. So we have now created for ourselves a means of quantifying or getting a number that is associated with our acidity or the basicity of a solution. So we can quantify acidity or basicity or alkalinity using what we call pH or even pOH, where the P in these terms relates to the fact that this is a 10 to the x exponential relationship. So let's talk about our quantification of acidity or basicity, which we call pH. So pH is a measure of the acidity of a solution and it is a logarithmic, specifically log base 10 dependence on the concentration of H3O plus present. Specifically, pH is equal to the negative log base 10 of the concentration of acid in your solution. This is our pH equation. And this negative log out front, like the negative aspect, this actually means that we would expect, if we were to undo our exponential increase, that as pH and concentration of acid are correlated, we would see a straight line decrease that is a direct proportionality. So we took a log base 10 of a 10 to the x exponential function so that we could get a straight line correlation, right? Chemists are good at reading straight lines. Trying to overlay some kind of function on a curve, like this one, this exponential curve, is something that we can't say with confidence. Whereas straight lines, those are something that we can definitely model with confidence using our R-squared statistical analysis. So if we were to look at the pH scale is a way of showing whether the solution is overall acidic or overall basic or alkaline. So because we see here in our little plot that as we have low concentrations of acid, our pH is higher. And as our concentration of acid increases, the pH drops. This means that low pH values, which can range from 0 to 14, the low values are our acidic pHs, and those are the ones that exist below pH 7. So when we talk about pH 7, we are neutral. This means we are neither predominantly acidic nor basic. So our solution would not be quantified or qualified even as being an acidic solution or basic if we're at a pH of 7 neutral. So then that means that as we increase our pH above a pH of 7, this is where our pH begins to get basic, alkaline. So here on the left, we have a low pH, meaning we're acidic. And on the right, a high pH, meaning that we are basic. So I know that we want to typically like trend in our brain, oh, if this is higher, then something else also has to be higher. I would agree with you. My instinct is like, shouldn't the concentration increase result in a higher pH or like a bigger number? And the answer is yes, but also no. And I'll show you why in a moment. So pH is the negative log of concentration of the acid particle in solution, H3O plus. Now we can turn this idea of pH kind of on its head, because what if we're looking at a solution that we don't necessarily expect to have any kind of acid particle in it whatsoever? Like, what if we are looking at a sample of, let's say, a base that's been dissociated in water or dissolved in water? So let's define the cousin of pH, pOH. This is the measure of alkalinity of a solution, and it has a log base 10 dependence on, again, concentration, but in this case, concentration of the basic particle. So I can say that pOH is equal to the negative log of concentration hydroxide ion. So the exact same structure in our equation. However, the difference is whether we are talking about an acid or a base. So if I were to make a similar diagram over here, like the pOH scale, it would be the exact inverse of our pH scale. So I'm going to follow the color coding of like purple blue means alkaline and green means neutral and red orange means like acidic. So the pOH scale would run from 0 to 14. Oh gosh, how can I fit these numbers in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, almost. Let's move that over, and 14. There we go. Okay, so in the pOH scale, this is an inversion of the pH scale. So we still have a neutral pH at, neutral pOH at pOH equal to 7. However, as our pOH increases, this is where we expect to see solutions that are more acidic. Okay, gonna have to bear with me here. as I do some color coding. There we go. So high pOHs means we are acidic. Whereas our low pOHs, that means we are basic. So all this is, like, I know it seems kind of confusing because they're really similar, but the idea is that pH and pOH are exact inverses of one another. All right, so here then in our low pOHs, we are basic. In our high pOHs, we are acidic. Low pOHs are basic. And then again, a pOH of 7, just like with a pH of 7, is neutral. So these are inverses. Now, pH and pOH are related to one another mathematically in a way that's more than just they are the inverse of one another. Because what does it mean to be the inverse of one another, right? Like if I know that my solution has a pH of 1, then my solution is highly acidic. So I would expect for it to be very poorly basic, right? So I would expect to have a high pOH because I'm really acidic and a low pOH because I'm basic. So how pH and pOH relate is through the following. pH plus pOH is equal to 14. So the sum of your pH and your pOH is 14. Now, where did this come from, right? I remember learning about pH and pOH and the relationship and being like, okay, fine. Like, I'll take your word for it, professor, I guess. And it wasn't until somebody showed me like where this 14 number and where these P's came from that I actually understood like why it was that we could describe acidity and alkalinity using these two terms and relating them through their difference. So let's think about what it means for a substance to be neutral. So if we are neutral, then we cannot have a predominance of acidic H3O plus or basic OH minus particles in solution. They have to be perfectly equivalent. This is what it means to be neither acidic nor basic. And if you think about a substance that perhaps has H plus and OH or acid and base particle involved in it, the one that you might think of is that of water. So I know that in Gen Chem 1, we talked about how water is, a polar covalent compound. It is not one that we expect to have any kind of dissociation because it's not any kind of ionic bond. But now that we're in Chem 220, we innately understand that everything exists on a spectrum. And that is true for these protonation, deprotonation equilibria that we've seen for our acids and bases so far. And water is a really interesting substance in that it autoionizes. So, what on earth does that mean? Autoionization of water? So, it turns out that in solution, liquid water, or if you prefer, HOH, has a very slight dissociation into H plus and OH minus. And I'm not going to write like H2O with H2O and show hydronium here. I'm going to simplify this. So if I were to look at like water itself dissociating, this would exist in some dissociation equilibrium where we split off into our acidic H and our basic hydroxide ions. Now, since this exists at an equilibrium, this ionization of itself, and if you prefer, why don't we show it with the full hydronium? That's why it's called autoionization. It does it to itself. So if one of these waters were to donate a proton to another, this would become H3O plus aqueous and OH minus aqueous. So this is kind of like the simplified version of water's dissociation. This is the more nuanced approach, understanding that water exists surrounded by a bunch of other water molecules, right? So we generate the hydronium instead of having free proton in solution. So it's like a technically kind of thing. Now, if we're talking about any process at equilibrium, this could be described by some K constant. And we have a name for that K constant. It is called Kw. Or the dissociation constant of water. And Kw has a known value. It's been measured in the lab. So let's write the expression for Kw. So that would be concentration of our dissociation products over our concentration of our reactants. However, here the reactant in question is just water, liquid water. So Kw is going to be a product of acid and base particle concentrations in solution. So this is the equilibrium constant for the dissociation of water. And the known value that has been recorded is 1.0 times 10 to the negative 14. So super, super tiny. This is why I wasn't like completely lying to you in Gen Chem 1 when I said that water is polar covalent and wouldn't dissociate and thus wouldn't behave like as a weak electrolyte or anything like that. It's because this is incredibly, incredibly small. So this equilibrium favors molecular water over it being dissociated into hydronium or hydroxide. 10 to the negative 14 is really, really tiny. Ooh, where is this headed? Like, what's my point with this? Remember, I'm trying to ask, like, why? Why does this relationship exist? Why is it that pH runs from 0 to 14, and so too does pOH, meaning like we can take the difference of one from 14 to get the other. Like, where's this 14 coming from? It's coming from the experimentally measured and verified K constant for the autoionization of water, or the water dissociation constant, Kw. So let's go ahead and derive this relationship. So I think in order to do that, I need to duplicate this page. All right. And now let's erase this duplication. That is a highlighter, not an eraser. There we go. There we go. All right. So we've got Kw is equal to concentration H3O plus times concentration hydroxide. And we know that Kw has a known value. So that's 10 to the negative 14. Concentration H3O plus, concentration OH minus. Now, if I were to take the negative log of both sides, or how about just the log of both sides? I would have the following, and that's algebraically legal because I did it to both sides. And remember, logs base 10 and exponents of base 10 are inverses of one another. So I've now got negative 14 is equal to log of the product of hydronium concentration and hydroxide concentration. Log rules state that if I have a product of terms inside my log, then I can rewrite that as a sum of two log terms, meaning I can say that negative 14 is equal to the log of concentration H3O plus the log of concentration OH minus. And if we recall our definitions of pH and pOH, remember pH is negative log base 10 concentration hydronium. And pOH is concentration, negative log of concentration hydroxide. Then if I move my negative over, I can replace these log terms in this expression that I got from Kw with my pH and pOH definitions. So let's divide this negative sign over. So this is going to divide into this and into this distributive property. So this is going to become 14 is equal to negative log concentration H3O plus minus log concentration OH minus, or if you prefer, and I do because I'm a visual person, 14 is equal to negative log concentration hydronium plus the negative log of concentration hydroxide. We have said that this is pH and this is pOH. So I can perform a little substitution by now arriving at the conclusion that therefore, triple dot, therefore, 14 is equal to pH plus pOH. And the utility of this is if you know the pH of a solution, we can find the pOH of solution using this and vice versa. So this is a very important relationship, and it comes from the entire pH scale, comes from the fact that we know the dissociation constant for the autoionization of water. So hopefully that made some sense. If not, that's okay. I'm never going to ask you to like redo this algebraic derivation here, but I do want you to see like where the 14 comes from and why it is I can make a statement like this. It's not just me pulling a rabbit out of a hat, right? It is me getting this from an actual property that we know about a neutral substance or a substance containing both acidic and basic particles in equal measure. That substance being water. So then how can we relate Ka, Kb, and Kw? Can we relate them? Let's find out. So recall, if we're talking about Ka, we are looking at some weak acid in the presence of water, creating hydronium, ion, acid particle, and A minus, which means that Ka is equal to concentration acid, hydronium, times concentration A minus, all over concentration HA. I could do the same thing for Kb, which is in reference to some base undergoing a dissociation in water to create BH plus and OH minus in solution. So Kb would be concentration hydroxide times concentration our protonated base over concentration of molecular or undissociated base. And then lastly, I can show the autoionization of water. So that is H2O in the presence of itself, where one of the waters acts as a Bronsted-Lowry acid and the other a Bronsted-Lowry base. This will create one acidic particle in direct proportion with one basic particle, one hydroxide. So Kw is equal to concentration H3O plus times concentration OH minus. All right, I'm gonna move some stuff around here while you copy and get this down in your notebook. So where am I heading with this? How can I relate Ka to Kb to Kw? Is there a relationship that exists? Is there a pattern that we're noticing? That's what we're striving for. Okay, so we've got here Ka, which is our expression of something acidic. We've got Kb, which is our expression of something basic. And then we have Kw, which is our expression of something that is neutral inherently. Let's see here. How can I perhaps simplify or substitute any of this so that I can, I don't know, do something interesting with Ka, Kb, and Kw? Let's see here. What if I were to take the product of Ka and Kb? Why am I looking at that product? Well, I know that Kw is both acid and base terms multiplied, and Ka involves an acid term, and Kb involves a base term. So what if I multiplied them? What would that get me? This would get me concentration H3O plus, concentration A minus, ooh, over concentration HA times concentration OH minus times concentration BH plus over concentration B. And if I were to maybe pull out concentration H3O plus and concentration OH minus, then this would allow me to leave behind the following terms. So this would be what's not H3O plus and OH minus. So this times this over this times this. So dissociation product, A minus and BH plus over undissociated HA and B. Okay. What if HA is water? And what if B is base water, right? Because water can be both. So what we would find if we were to do this, it's going to get like a lot of kind of word soupy here if we were to substitute in all of our hydroxides, H3O pluses, and waters. But what we would find is that all of this stuff in the context of one substance dissociating would result in Kw being equal to Ka times Kb, meaning this quotient here, if our HA is HOH and our B is HOH, if we do a bunch of algebraic substitution, which my iPad's dying, so we won't, we would find that Kw is equal to the product of Ka and Kb. Because notice this is Kw, and all of the stuff that's highlighted here in yellow would reduce to 1. We can look at this again when we have a conversation about conjugate pairs, which we haven't really discussed yet, even though we've seen them this entire time. But this is kind of nice for us because if we know the Ka of some weak acid, then its basic form that exists in solution, which we'll talk about, will have a Kb that could be solved by understanding what Kw is. So this will be important. When we want to make pH, pOH determinations or pKa, pKb determinations for a weak dissociating acid or base. So we'll revisit this, but the main idea is that Ka, Kb, and Kw are all related. And it comes from the fact that water itself contains both an acidic and a basic particle, and its equilibrium constant for that dissociation equilibrium, that ionization equilibrium, that involves a 10 to the negative 14, which is where our pH scale gets this derivation from 0 to 14. Okay, so we are going to be we're going to be measuring pH a lot. You have done so thus far in lab for like the past 4 lab meetings, I think. But now you have a better sense of what pH is, right? It is a log scale of how concentrated your acid particles or base particles are in your flask. So coming up on the horizon for us is thinking about, again, the utility of this piece of information here. Because again, this is talking about some weak dissociating acid or base. And that means that when we look at our dissociation equilibrium, we are innately looking at an acid and base existing as both dissociation products. So we'll talk about that. We're going to get into buffers and the Henderson-Hasselbalch equation coming up in our next lecture video series.